In this video, we discuss the intermediate value theorem. We'll look at some examples as well, and we'll use this as an opportunity to discuss some types of discontinuities. We've discussed these before, but we haven't labeled them. We'll define the terms removable and non-removable discontinuities, jump discontinuities, oscillating, and unbounded discontinuities. So here's the theorem. It says if f is continuous on the interval from a to b, and f of a is not equal to f of b, and k is between f of a and f of b, then there exists at least one c in the interval of f between a and b, such that f of c is equal to k. Let's make sure we understand what that says. First, it says that our function f is continuous on a closed interval. So just as a review, we say that a function is continuous at c if you can just plug in c to f to get the right limit. And we say that f is continuous on an interval if you can draw f on that interval without lifting up your pencil. Formally, that just means that the function is continuous at every x value on the interval from a to b. Now, when we say that a function is continuous on the closed interval a from a to b, all we're saying is that when we plug in a and we plug in b, the limit from the left and limit from the right exist as appropriate given our curve. So let's say that at x equals a, our function value f of a is up here. And then at x equals b, our function value is down here. Either way would be fine. I just chose to make f of a larger than f of b this time. And our function is continuous on that interval, so that means I can draw it without picking up my pencil. But if it's continuous in the closed interval, we're saying it's continuous from the right at a. So the limit as x approaches c from the right of f of a is f of c. Or excuse me, f of a. Basically, it has to be continuous from the right at the left endpoint, because we're approaching that point from the right. And it also has to be continuous from the left at the right endpoint. So you're able to just plug in those values and get the right thing. So we say it's continuous in the closed interval if those are both true, and f is continuous on the open interval. Between, again, that just means you can draw the whole curve without lifting up your pencil, or pointwise. For every x value in the interval from a to b, you can just plug in the x value, and that'll give you the right value of the limit. So provided that that's true, and those two function values are not the same, and k is some number between f of a and f of b, so it's some number in here, then there exists one c in the interval from a to b, such that f of c equals k, or in other words, f of x equals k has a solution on the interval from a to b. That means I can find an x value that has the corresponding y value, the y value I'm interested in. And we can find at least one x value that will satisfy that equation. There might be more than one. So let's look at a particular example. Now this is an existence theorem. It just tells us that there's a solution. It doesn't tell us what the solution is. And the theorem applies provided that these things are true. So if someone asks you to use the theorem to show that an equation has a solution, you have to check these three things. Now, in every problem, it's going to be different. Like sometimes we'll have an interval from a to b that's given to us, and sometimes we'll have to just guess what that interval from a to b is. but we need to check three things. That if that f is continuous on the interval of interest, that the function values are different, and that k is between those two function values on the endpoints. The function values are different in the endpoints. That k is between those two y values. Then there's just at least one x value that maps to that y value. So here is our function. We're going to use the theorem to show that this equation has a solution. In this case, our f of x is this exponential plus a polynomial, and our k value is the right-hand side there. And we want to show that that has a solution. Well, first I need to know that that function is continuous. Well, exponentials are continuous all the time, and linear functions are continuous all the time. So the sum is going to be continuous. So we'll just state that. So we'll say since f is the sum of an exponential and a polynomial, f is continuous on the entire real line. And then I need an interval from a to b where I think we might have a solution. Now, to infer that interval, I can use what I know about each of these functions. I don't actually know what this polynomial plus this exponential function looks like without getting a graphing calculator out and graphing it. But I do know what the exponential looks like, and I do know what the linear function looks like. So I can sort of think about those and use my knowledge of those to infer an interval, or at least to graph those functions and then infer an interval. So I'm going to take that equation. I'm going to write it as an equivalent equation by subtracting x from both sides. And now I'm thinking of this as two separate functions. I'm thinking of this as a function y1 and this is a function y2. Now the solution set of this equation is the same as the solution set of that equation. So if I can find the solution sets of this, I will know the solutions of this as well. I'm choosing to write it this way because I know what this function looks like and I know what this function looks like. So I'll graph y1. Y equals e to the, or 2 times e to the 3x looks like this. And x equals 0, y equals 2. And when y equals negative x, it's just a line with a slope of negative 1. And the solutions of this equation are just where this curve crosses this curve. That's actually a point. The solution is that corresponding x value of that point. So it looks like our x value is negative. It's not very large in magnitude. It looks like it's close to 0, but it's definitely not 0. And I just need to figure out what that x value is. Since I know that my x value is just a smaller negative number, I'm just going to choose a negative number over here to the left of that sort of implied x value, and then we'll choose x equals 0 on the right. Let's substitute x equals negative 2 as a potential a for our interval from a to b. So that is 2 times e to the 3 times negative 2 minus 2. So I have 2 times e to the negative 6 minus 2, which is approximately negative 1.995. I would typically use a calculator to compute that. I actually did this example earlier, so that's why I knew what the answer was. And then f of 0 is 2 times e to the 0 plus 0. So we just get a 2. So at x equals negative 2, our y value is nearly negative 2, and at x equals 0, our y value is 2. So negative 2, negative 1.995 is on our graph. And x equals 0, y equals 2 is on our graph. And we know that f is the sum of an exponential and a polynomial, so it's continuous. I don't know exactly what it looks like between this point and this point, but I know that when I draw it, I can draw it with a smooth closed curve. So it might look something like this. Of course, I'm just guessing, but it might look something like that. Now we have enough information to use the theorem to prove that f of x equals 0 has a solution. So we'll say since f is continuous on the interval that we just came up with, -2 to 0, and our k value is 0. So y equals 0 is just the x-axis. That 0 is in between the y value at this point, which was approximately -1.995, and the y value at this point, which was 2. So 0 is in between those two y values. And of course, f of -2, that was that number, is not equal to f of 0. Since all of those are true, our theorem says that f of x equals 0 has at least one solution on the interval from 0 to 2. Or -2 to 0, I'm sorry, by the intermediate value theorem. Now this is just a guess for the graph, and I'll admit I actually graphed this in advance. But let's look at the graph on desmos.com and see what it looks like. So there's our exponential graph, y equals 2 times e to the 3x, and there's a graph y equals -x. The point of intersection is right there, approximately. Looks like x equals -0.5 and y equals 0.5. Something like that. Now we're interested in the sum of those two functions. So I'm adding all of the y values on this line to the y values here. So we should get this. These y values plus these y values are supposed to be these y values. I'm a little bit concerned here. Sorry about that. I was concerned because I was thinking about adding these two, but I'm not adding 2e to the 3x and -x. I'm actually adding 2e to the 3x and +x. So if I draw this graph, y equals x, and I think about adding these two functions together, this function, oops, this function and this function, I'm taking these y values and adding something that's very small and positive. So it's going to be linear. It's going to be approximately linear when x gets sort of beyond -2, from -infinity to -2. It's going to be this plus a very, very, very tiny positive number. And then on the interval from -2 to 0, I'm going to take this line and I'm going to add these y values, and they're starting to increase relatively rapidly. The exponential is sort of coming off of the x-axis and moving toward that point of intersection and that y-intercept on the y-axis. So I'm going to take all of these y values, which are negative, and I'm going to add these y values. And then I'm going to take these linear values and add these very, very large y values. So putting those together, I get something that looks like this. That's the graph of the function that we're interested in. And the point of intersection of this graph with the x-axis, that's where y equals 0, is the same as the point of intersection of the exponential function and y equals -x. So I'm expecting the answer to be something like that -4.77 or -0.477. And that's what it looks like. -0.477 is the root, according to desmos.com. Now you can say, okay, well, what does that have to do with the theorem? Well, the theorem says that that function is equal to 0. And again, a function is equal to 0 when it crosses the x-axis, because y equals 0 looks like this. Y equals 1 is a horizontal line raised up 1 unit. Y equals 0 is a horizontal line on the x-axis. Y equals -1, the horizontal line below the x-axis. So 0 is that x-axis. That function crosses y equals 0 or the x-axis at that location. So we know that that equation has a solution at that location. But the theorem says, okay, if this function is continuous on the interval from -2 to 2, and it is because it's the sum of an exponential function and a linear function, and the y value at -2 is less than y equals 0, or excuse me, y equals 0 is in between the y value at -2 and the y value at 0. And let's look at those two y values. There's the y value at -2. It's giving me a hard time right now. Okay, let me do this. I'll add a subscript on it so that it recognizes it as a separate function. There's the y value at x equals -2, and then the y value at x equals 0. The y value that we're interested in is y equals 0. We want the function to be equal to 0. So 0 has to be in between those two y values, and it is. 0 is between -2 and 2. Y equals 0 is right there. Then we're saying if the function is continuous and it goes from this point to that point, then it has to cross the x-axis at some point. And it turns out that it does cross the x-axis at approximately -0.477. Just to illustrate that, let's plot those 2 points. So there, if I graph it on that interval from -2 to 0, that's what we see. Function's continuous. It passes through y equals 0. And therefore, the equation f of x equals 0 has a solution, and we can read the graph to infer what the solution is. Now let's look at a few examples where the intermediate value theorem does not apply. So here's an example. This might be a quiz question. If possible, use the intermediate value theorem to show that this function or this equation has a solution. If it's not possible to use the theorem to show the result, explain. And so we've got a function that is a rational function. State the function right here. And just from looking at it, we can see that it has a discontinuity. It has an x minus 3 as a factor in the numerator and denominator. If this was a third degree polynomial, if we just distributed and we had, a constant times x cubed plus a constant times x squared and so on, we might have to factor that to see it. But since it's already factored, we can see that we've got a common factor in the numerator and denominator. This function is actually the same as the function x minus 2 squared, as long as x is not equal to 3. So this function is going to look like this parabola everywhere except for at the point where x equals 3. We can graph that. When x equals 2, the y values will equal 0. And then at x equals 1, our y value would be 1 minus 2 is -1, -1 squared is 1. And at x equals 3, the y value would be 1, but it's not 1 because x equals 3. The function's not continuous there, it's not defined. So we're going to have an open circle there. And our graph looks like this. It's just a parabola with a hole in it at x equals 3. Now, we want to use the intermediate value theorem to show that that equation has a solution. So in this example, our function f of x is this function. This is our value k. And remember what we have to show, or we have to say, that the function is continuous on the closed interval. The function values on either side of that interval are not equal to each other, and k is some number between a and b. And k is given to us, k is equal to 1. So I'm interested in figuring out where this function is equal to 1. Well, I think that we can look at the graph and see that when x is equal to 1, y is equal to 1. We can also plug in 1 and see that when x is equal to 1, y is equal to 1. So we know that the equation has a solution, but we want to use the intermediate value theorem to show that. So we need the function to be continuous on an interval from a to b, and we want that interval to include x equals 1. So let's just choose the interval from 0 to 2. I'm going to focus on this interval here. I know it's kind of overkill because we already know the equation has a solution, but we're trying to illustrate that the theorem can be used to show that the equation has a solution. So we can say f is continuous on the interval from 0 to 2. That's the part of the graph that I'm looking at. X equals 0 on the left to x equals 2, going from there to there. F of 0 is equal to 4. F of 2 is equal to 0. So our k value is between f of 0 and f of 2. K equals 1, that's between this 0 and 4. So that means our theorem holds. So this is true and this is true. So f of x equals 1 has a solution on the interval from 0 to 2 by the intermediate value theorem. And that's it. So we are able to use the theorem to show that the equation has a solution, but we had to choose an interval that includes x equals 1. Now, if the problem statement was just a little bit different, let's say that if possible, use the intermediate value theorem to show that f of x equals 1 has a solution on, let's say, 2 to infinity, or let's say 2 to 10, to give us a finite number. A is 2 and b is 10. So we would evaluate the function at 2, we'd get 0. Evaluate the function at 10, we get 10 minus 2, it's 8 squared, so we get 64. And then we'd say, can we use the theorem to show that f of x equals 1 has a solution? Well, we can't, because on the interval from 2 to 10, we have a discontinuity at x equals 3. So we'll say it's not possible to use the intermediate value theorem on this interval because f has a discontinuity at x equals 3, which is on the interior of that interval. These are x values that are giving us. We're starting at 2 and then we're going to 10. And now we can also see that on that interval, the equation does not have a solution because the function gets very close to 1, but it never actually reaches 1. and we get very, very close, we like skip that point y equals 1. We actually have all of the y values between 1 and 64, or between 0 and 64, except for y equals 1. So the intermediate value theorem doesn't hold, and because of the discontinuity. Now, this type of discontinuity where the limit exists, but the function is discontinuous there, is called a removable discontinuity. We call it removable because we could remove it just by redefining the function. We could say, let's let f be equal to this as long as x isn't equal to 3, and let's let f equal 1 when x equals 3. That would just allow us to fill in that little hole that would be removing the discontinuity. So we'll say a removable discontinuity is an x value where the limit exists, but f of that x value, let's just say f, the next value is c where the limit exists, but where f of c is undefined. Basically represents a hole in the graph. We call that removable. So with a removable discontinuity, we could accidentally skip the y value that we're interested in. And then in that case, the function might, or the equation may not have a solution. In this case, we skipped this y value at x equals 3, but we didn't. We covered that y value at x equals 1. So as long as our interval includes x equals 1 and does not include 3, we're good to go. The theorem holds because the function's continuous. And we can always choose a and b so that our y values are on either side of y equals 1. Okay, let's look at another example. Now we've talked about limits that do not exist. Each of those limits that just does not exist corresponds to what's called a non-removable discontinuity. It's an x value. Let's say an x value c where the limit as x approaches c of the function does not exist. And there were 3 types of non-removable discontinuities. Jump discontinuities. That's where the limit from the left and the limit from the right are different from each other. Maybe here at x equals 3, you get one limit on this side. Maybe the y values are approaching 2. And then maybe on the other side, the y values are approaching 3. That's a jump in the graph. That's called a jump discontinuity because the limit from the left, of the function is not equal to the limit from the right. Limit from the left of 3 is not equal to the limit from the right of 3 for that particular function. In this case, we're saying that 2 is not equal to 3. Now, if we are looking at an intermediate value theorem problem, let's say that this is our function. This is y equals f of x. Maybe the problem statement says, if possible, use the intermediate value theorem to show that f of x equals 2.5 has a solution. Well, we can see graphically that f of x equals 2.5 has a solution. It's whatever that x value is right there. But is it possible to use that theorem to show that that's true? Well, I can show that that's true as long as I'm on this continuous piece. I don't want my interval to include the value x equals 3, because then I would have a problem at the jump discontinuity. Or at least it can't include any values less than 3. So we could use the interval from like 3 to 4 or 3 to 5, something like that. It really just depends on what that function value, well, what this function value is. This is y equals 2.5. Depends on what this x value is. Since I didn't draw my graph to scale, it's kind of hard to see. Let's just say that that's 4. So we'd say yes, on the interval from 3 to, let's see, 4.5, the theorem holds. Because f is continuous on the interval. F of 3 is 3. F of 4.5 is some other number. I'm not really sure what it is, but it might be about 2. And those two values are not the same. And then we needed y equals 2.5 to be in between those. And I'm using 2.5 because that was what was given in the problem statement. The f of 4.5, which is approximately 2, and f of 3, which is 3. Since the theorem holds, that means that f of x equals 2.5 has a solution on that interval. By the intermediate value theorem. So we would just have to choose an appropriate interval. Now, if they asked us, does the theorem hold on the interval from 2 to infinity or 2 to 6? Well, we have a jump discontinuity there. And even though the equation has a solution, the theorem cannot be used to show that that equation has a solution unless we choose a smaller interval. Maybe my graph looks like this. This type of discontinuity is called a removable discontinuity. That x equals 3. And so the intermediate value theorem cannot be used on any interval containing 3. Problem statement might say something like, does f of x equals 5 have a solution? Can we use IVT to show that f of f equals 5 has a solution on some interval? I'm gonna say no. That function is never equal to 5. It gets very, very close to 5, but it's never equal to 5. So no, we can't use the intermediate value theorem to show that that equation has a solution, because first of all, it doesn't have a solution, and second of all, the theorem doesn't hold because the function's not continuous at 3, which would have mapped to 5 if there wasn't a removable discontinuity there. Now with the jump discontinuity, we might accidentally skip over the y values that we're interested in. So here's another example. So maybe our equation, or maybe our graph looks like this. This is 2 and that's 4. So let's say this is x equals 3 as well. Now in this example, x equals 3 corresponds to a jump discontinuity. Okay, does f of x equals 3 have a solution? And of course, the answer is no. If I graph y equals 3, we've skipped that value. We skipped all the values between y equals 2 and y equals 4. And we might be asked, can the intermediate value theorem be used to show that f equals 3 has a solution? And we'll say no, because we have a jump discontinuity. Problem is we skip those y values between 2 and 4. Now, if this parabola, instead of pointing up, had been pointing down, the equation might have a solution, but we couldn't use the theorem to show it, at least not on any interval, including 3. We could use the interval to the intermediate value theorem to show it on that continuous piece. But because the function is discontinuous and because we have the jump discontinuity, we don't get all the y values on any interval. We get y values from -infinity to 2 and y values from 4 to infinity. Now here's another example. Now in this example, we've got f of x equals, let's say 2 minus 1 over x minus 4. So this looks like the graph of 1 over x. We flipped it upside down by multiplying by the -1. We shifted it 4 units to the right by subtracting 4 from the x values, and we added 2 to the graph. So it's just that y equals 1 over x graph moved around a little bit. Well, we might notice that this function takes on every y value except for y equals 2. So we say, does f of x equals 2 have a solution? No, it doesn't. Say, does f of x equals k have a solution? Where k is a real number and k is not equal to 2. Okay, well, yes. Any value of k will work. K equals 4, k equals -1, k equals -10. Like any value that's obviously not -10, that looks more like y equals -1. This looks like y equals 1, -1, this y equals 1. That would be supposed to be y equals 4, but unsuccessfully it doesn't, it looks like it's got a little bit of a slope to it. I was trying to draw a horizontal line, that didn't really work out, did it? It's supposed to be y equals 4. But all of those have solutions. There's an x value that maps to that y value. There's an x value that maps to that y value. There's an x value that maps to that y value. This x value is that one right there. The x value that goes with y equals 1 is that one right there. The x value that goes with y equals -1 is that one right there. So each of these y values has a corresponding x value. So f of x equals k does have a solution as long as k is not equal to 2. And we can use the intermediate value theorem to show that because f is continuous on the interval from negative infinity to 4 and the interval from 4 to infinity. So we'll always be able to use the intermediate value theorem in those cases. We just have to be careful about including that x equals 4 in the interval. X equals 4 is an infinite discontinuity. Sometimes it's called an unbounded discontinuity. And because we have an infinite or unbounded discontinuity, the intermediate value theorem does not apply. So we said, in order to apply this theorem, the function has to be continuous on the interval of interest. We have to find an interval. If the interval is not given to us, we have to find an interval where that function is continuous. We've got to be careful about all those possible types of discontinuities, whether they're removable or they're jump discontinuities or they're infinite or unbounded discontinuities. The last type of discontinuity that we discussed was related to that sort of rapid oscillation between a number of values. So let's say that f of x is equal to 2 times sine of 1 over x minus 5 plus 3. So this is going to oscillate rapidly as we get close to x equals 5. We're taking a sine function which oscillates between -1 and 1, and we're multiplying it by 2. So it's going to be twice as tall. And then as we get closer and closer to 5, it's going to get there, like, it's going to be denser. So x equals 5 is an oscillating discontinuity. So the intermediate value theorem can be applied on any interval that does not include x equals 5. So someone might say to you, if possible, use the intermediate value theorem to show that f of x equals 4 has a solution. And let's pick an interval. On the interval from, let's say, 2 to 6. So on an interval including x equals 5. Well, we can look at the graph and see that we're actually going to have infinitely many x values that cause that function to be equal to 4. Because this function is oscillating rapidly between 2 values. Sine normally ranges from -1 to 1. We multiply by 2, it ranges from -2 to 2. If we add 3 to that, the range is 1 to 5. So our values are all between 1 and 5. And my function is continuous at every x value except for 5. So while this function or this equation does have a solution, we have to be careful. This question says, can I use the intermediate value theorem to show that this equation has a solution on this interval? Well, only if the function is continuous on that interval. And it's not continuous on that interval because there is one x value on the interval from 0 to 2 that's a problem, and that's x equals 5. The rest of the time, at any other x value, we would be fine. So if we chose an interval like 2 to 5 or 2 to 3, we would be able to find lots of x values that would map to y equals 4, but we'd have to make sure to avoid x equals 5. But the function itself does have infinitely many solutions on that interval. Or not the function, the equation has infinitely many solutions on it. Okay, I think that's it. We can look at some of these graphs on Desmos. I want to show you sort of prettier graphs. But if you get to know these graphs, if you get to know these functions, you can graph them by hand. So this is the first example that we looked at. We were asked to see if the intermediate value theorem could be used to show that f of x equals 1 had a solution. And we said we have a problem here at x equals 3, we've got a removable discontinuity, but we can show that the function or the equation has a solution, or f of x equals 1 has a solution using the intermediate value theorem, as long as we choose an interval that includes x equals 1, and that interval does not include the point of discontinuity. So there's an example of a removable discontinuity. And here's the oscillating discontinuity that we talked about. This is 2 times sine of x minus 5. So if we graph x equals 5, we can see it. The function oscillates rapidly the closer that we get to x equals 5. And the y values are all within plus and minus 2 units of 4. So our y values range from 2 to 6. We can actually find a solution to the equation f of x equals any constant, as long as that constant is within the range of the function 2 and 6. But we can only use the intermediate value theorem to show that that equation has a solution if the interval does not include x equals 5. And then with the unbounded discontinuity, like here's an example of an unbounded one. And so this particular function has a horizontal asymptote of y equals 1 and a vertical asymptote of x equals 3. And that's what our function looks like. We can use the intermediate value theorem to show that f of x equals k has a solution. As long as k is in the range of this function, the range is -infinity to 1. So the y values on the graph go all the way from -infinity all the way up to 1, and then they stop. That's the maximum of the function. But we need to be on an interval that does not include this x equals 3. Because x equals 3 is an unbounded discontinuity. That means the function is discontinuous there. So I think that's it. Now, one other thing I should summarize with. And I may have already said this before, maybe not. Non-removable discontinuities. These are just x values where the limit does not exist. There were 3 types: jump discontinuities, infinite discontinuities where the function goes to plus or minus infinity on either side or on both sides, and then oscillating discontinuities. All 3 of those are non-removable because it doesn't matter how we redefine the function, we can't make it continuous. A removable discontinuity is an x value where the function value does not exist, but the limit itself exists. So there's basically a hole in the graph. You'd be able to fill in that hole and make the resulting function continuous. So that's why we call it removable as opposed to non-removable. Okay, I think that's it. Now remember, when you're applying the intermediate value theorem, you want to check all 3 of these conditions. If all 3 of these conditions hold, then there's a equation that has a solution. Sometimes the interval is given to you, sometimes it's not. But make sure you check continuity on the given interval and that those function values are different and that k is between those function values. And then one other thing, I mentioned it while we were looking at the pictures online. In order for k to be between those 2 function values, k has to be in the range. So if you're looking at a function like this exponential function, 2e to the 3x, the range is 0 to infinity. Just make sure that the y value that you're interested in is actually in that range. If you try to set 2 equals e to the, or 2 times e to the 3x equal to -5, you're never going to be able to find some exponential values that give you a value of -5, because these guys are all positive and they can't ever equal -5. So think about continuity, think about range, and make sure you check all 3 conditions, and then you should be good to go.